We'll now move into section 1.7. There is no homework that comes from this section. This is purely a good for your information section. So this will be a fairly short video, and you've already seen so much to do with limits, and we've never actually given the precise definition as the book calls it. We've always just used that intuitive definition, and that was always enough. That intuitive definition got us through the graphs, and then that allowed us to understand and see the limit laws to then get us into the equations and get all the different techniques. But all those limit laws needed some real definition for them to work. And that's where this comes in. So this is just going to re-support everything we've said. It's also a good idea to watch this just to get a little more practice. Part of Calc 1 is, of course, to learn the ideas of calculus, but this is also a really, really good class to just expand your mathematical maturity, to expand just your general understanding and ability to see and understand mathematics. And that's exactly why we're going to go through this. So again, just for your information, if you do get a little bogged down and it doesn't quite make sense, it's okay. What you just saw with part 3 from 1.6, that review, that's what you're going to need for your quiz that's coming up. That's what we're going to need as we continue to move forward and talk about continuity as our next big topic and the derivative as the next big topic after that. So you'll be fine as long as you're doing well with those problems, but this is still a good section to look through. Okay, so the precise definition of a limit. We have our limit notation. The limit of f of x as x approaches a equals L if, and this is where it gets a little ugly, so let me write it out first. If, given a value epsilon greater than 0, this is a little fancy math notation that stands for there exists. So if someone, this is kind of like a challenge, someone challenges you by giving you some epsilon value greater than 0, then you have to come up with, there has to exist a delta value that's a little bit different than the triangle delta that we've seen. It's the lowercase version. Then there exists delta ST, that's just my own notation. That stands for such that, and you'll see me use that a lot throughout the class. So there exists a delta such that for every x such that absolute value x minus a is less than delta, this forward arrow, that in math stands for implies. So every x such that absolute value x minus a is less than delta implies absolute value of f of x minus L is less than epsilon. And that feels like quite a mouthful. There's a lot of, your Greek letters, so it just really almost sounds like a word jumble sometimes. But let's just take a few moments to try and dig in and see what this is actually telling us and how this works. Now again, we're still kind of working from that intuitive definition and seeing how this ends up being the same thing. So let me just draw a quick little graph. So here's some function f of x. Don't care what this x value is. Generically, we'll just call it a. And that however our function works, whether it actually comes together and touches or not, and then whether it goes up or down from there, but this point over here, the y that corresponds to that would be our value L. So that again, as we approach this x-coordinate A and you start following the points up here, I'll just make it an open circle for this one, that this is the L. So everything that we've seen, that if this was our graph, whatever these numbers are, if this is x is 2 and that's y is 4, whatever it is, we understand that that is the limit that we are setting up. So how does this definition give us that answer? Well, one quick thing before I keep pounding away with this picture is to get a little bit more of an understanding on what is absolute value. Because for so many of us, so I'm just going to jump to the bottom of the page here, because for so many of us, all we know about absolute value is that everything is positive. So that the absolute value of minus 4 is 4, but the absolute value of positive 4 is also 4. So what is the absolute value really? The absolute value of x, and really should be set up as the absolute value of x minus 0. Whenever you have this expression, you are looking at distance. So minus 4 and positive 4, both of these, how far away are they from the number 0? Because in this form, I could think of minus 4 as minus 4 minus 0, and I could think of 4 as 4 minus 0, so that both of them satisfy this situation, and that literally x minus a in absolute value would be the distance between x and a. So both of these, why is the answer 4? Because direction doesn't matter. Negative 4 is 4 units to the left of 0. Positive 4 is 4 units to the right of 0, but they both have that same distance of 4. So this whole idea up in this definition, this is all talking about distance. So the challenge is, I'm your opponent. I give you some epsilon, and then you have to respond with some delta. And what's so special about these, the epsilon I give you is giving you a distance, the maximum you can go away on the y scale from the limit value L. That's what epsilon does. But then that limit value is true when you can provide me the delta value so that my distance from A, no matter what point I pick that is within that distance from A, the y value is within the epsilon distance of L. This is still a mouthful. That's why I said it at the beginning. You're trying to open up some doors, trying to get used to some new math notation and lingo. Even if all you get out of this is just a little bit of the math symbols and a little bit more from absolute value, it's worth your while. But let's put all that together. So my first challenge, I give you an epsilon value and I make it fairly big. So that for f of x minus L to be less than epsilon, my y value would have to be within a distance of epsilon. So going up and down, up epsilon and down epsilon. And when I give you that epsilon, what I'm doing here is I'm kind of opening up a tunnel. So now you, as my opponent, you have to now look on the x-axis. How far left and right from A can you go so that all the points end up inside of this tunnel I created? Well, if you start going out too far, if you go out too far to the left, these points are outside of your tunnel. If you go outside here too far to the right, these points will be outside of your tunnel. And it's not trying to find the biggest delta, but just any delta, so all the points will be inside this tunnel. So let's do this. This will be minus delta, and this will be plus delta. And notice, when I look at this tunnel going up, all of these points, their y values are inside of this tunnel that was created by epsilon. But that's not where it would go. This needs to be true for any epsilon. So if I gave you a smaller epsilon, I don't want this picture to get too messy, so I'm going to do something similar, but now I'll use the red pen, because now I'm going to give you a tiny value of epsilon. Okay, so I gave you a big value of epsilon, you were able to find me a delta, so the game continues. I give you a tiny value of epsilon. So with that tiny value of epsilon, now it's like epsilon is 0.1. Now I'm creating a tunnel, a very, very narrow tunnel. So since my epsilon tunnel is very narrow, look back here, the original delta we used for the first epsilon, now I'd have points here that were inside the first tunnel, but are outside of this new tunnel with the red pen. So now I would need a smaller delta. Smaller epsilon typically leads to a smaller delta. And notice, now I need all the points to stay inside the red. I can go a decent little distance to the right staying inside the red tunnel, but I can only go a little bit to the left before I fall outside of that tunnel. So I'm going to need a very little epsilon value, so that way now, when I translate that up, I'm sorry, I slightly wandered. That should be a little bit more like this. But either way, Now that vertical tunnel I just created does all the points that are inside that vertical tunnel are also inside this horizontal tunnel. So this is what we've always been pointing out through the intuitive definition. It's all about looking from both the left and the right. Is the graph coming together? For you to be able to do this, I could even make smaller epsilons and you could just give me smaller deltas, but it'll always work because the graph is coming together here. So let's just finish this up quickly. Let's look at why this doesn't work in a situation where the limit does not exist. So if I had something like that, from our experience, there is no L. There is no limit. Whether this is filled in or open, I'll make it filled in, but there is no limit as x approaches a. From the left, we're at this y value. From the right, we're up here at this y value, and these two don't match. So this is exactly a situation where the limit does not exist. You know, as x approaches a. I should definitely make that note. Just as x approaches a, that's where the limit doesn't exist. We'd have limit values out here and here, but just right here is where we're having the trouble. And I don't want to make a big mess here, but if I gave you too big of an epsilon and I gave you too big of a tunnel, you might be fooled to thinking that you do have a good limit. Maybe you think the limit is 1.5. If this is 1 and this is 2, and you're thinking about splitting the difference, well, if the epsilon is big enough, you can make this work. But if I, again, think this is my limit, but I give you a little epsilon, look at this little tunnel. It doesn't matter how big or small you make delta, there are no points that are inside this tunnel. Well, if you think this, well, maybe then this is the wrong limit. So now you think this should have been the limit, and you make your tunnel, and again, even if you make it small, well, now you can go a little bit to the right and you'd be getting points inside this tunnel. But if you go any bit to the left, you'd be having points down here, which are not inside this tunnel. So that can't be the limit. And the last try, if we try this one as the limit, well, now we get the flip-flop problem. Now I'd make my little tunnel. And now, as I'm on the left side of A in a close proximity, I'm inside that tunnel. But as soon as I jump to the right side of A, I'm up here and I'm outside this tunnel. So again, one last time, this is not an easy video. This is for a lot of people taking Calc 1. This is some pretty heavy duty notation. And that's why I hope it makes sense that we did this after we did all that other limit work. So this is just good for your information here. Not to worry if this was a little bit tough. No homework from here. This is not coming up on any test or quiz. Just, again, a little reinforcement, a little extra good stuff for you to see.